Okay, thanks David for the introduction, and it's great to be back and see many familiar faces and friends in the audience. So I think many of you are familiar with the gains of supervised deep learning in the last few years, primarily in three areas: vision, speech and audio, and natural language processing. And where these gains have typically been made are in domains where large labeled data sets are available. And of course, this has gone hand in hand with complicated architectures, which are prone to overfitting. So the downside is that most of the data that's readily available is actually unstructured and unlabeled. And this problem of obtaining large labeled data sets is what I think has largely limited deep learning's applicability outside of these three big domains. And labeling data, as many of you know, requires a lot of effort for those of you who have been grad students or postdocs and have been involved in large labeling efforts. So today, I'm going to tell you about how to acquire this sort of scale of data without the labeling effort. So let's look at a few existing approaches. Back in the old days, David referenced, like 2004, 2006 here in Toronto, we all knew about unsupervised pre-training. That was a cool thing at the time. These days, there's supervised pre-training. And the idea here is that you have a large labeled data set that is not necessarily the same as the particular domain you're interested in. So for example, you have ImageNet, 1,000 categories, about 1 million images, and a generic visual recognition data set. But maybe you're interested actually in, say, bird species detection, and you have a much smaller labeled data set. So the idea is you pre-train a deep net on ImageNet, and then you go and you realize your outputs are different, right? So now instead of having generic object categories, you have bird species. So you take off the top layer, you replace the outputs to reflect your new categories, and then you train the top layer. And some people might go a step further and actually do continued training, or what we call fine-tuning, using the smaller labeled data set. And this is certainly a reasonable paradigm when you have good domain fit between the large labeled data set and the smaller data set of interest. So for example, in visual object recognition, you're going to find in the ImageNet data set lots of birds, right? So you'll be able to learn features like wings and feathers and beaks and all those sorts of things that you would expect to show up in your domain of interest. Now, when your data is very, very specialized, so for example, you're dealing with images from a microscope, or if you're going out to, say, a remote sensing project, you're not going to get a good domain match between a generic data set like ImageNet and your specific domain. So maybe you're working with a specialized sensor. People are working in this space now with multispectral or hyperspectral. You're not going to get a great return from pre-training on ImageNet. So what other people also do is look to an alternative of labeling more data, which is synthesizing data from some sort of rendering engine. So, for example, it's been quite popular these days to work with video games. You see at the top, Grand Theft Auto, which is actually such a great graphics engine that it has actually reasonable match with the real world. So you can do semantic segmentation here, where you're labeling a street scene just by training a model on an essentially infinite amount of data coming from Grand Theft Auto. And this is a paper from UBC, which generated a splash. A couple years ago, we worked on a project where we were doing hand pose estimation. So for example, in gesture recognition, using a synthesis pipeline, for example, Poser, which is a sort of a generic way to generate labeled data. We know exactly the locations of the parts of interest on the hand. And again, we could generate essentially an infinite amount of labeled images. We did essentially semi-supervised learning, where we had a very tiny amount of labeled real data and an infinite amount of synthetic data. So again, this might not work if the simulated environment is not a good match to the real domain of interest. If you're working in a specialized application, you would, of course, have to have access to a simulator that would be reasonable for your problem. So this brings us to something that's even more popular, which is dataset augmentation. So this is something that's essentially ubiquitous in computer vision, where you go and, because you have knowledge of this space, we generally, as people, understand how images should transform, you go and apply a whole bunch of hand-coded transformations to your data set at the level of the input, right? So you can noise your images with using appropriate, say, JPEG noise models. You can crop them, you can scale them, you can rotate them, and this will generate a much larger existing data set and allow you to learn to be invariant to these types of sources of variability. And of course, as I mentioned, it's ubiquitous in vision, but certainly not for other domains. For every new domain you want to tackle, you would have to go and code up these transformations, implement them, and test them, and so forth. So what brings me to the topic of today's talk is thinking about embedding this augmentation procedure into the architecture, not doing it at the level of the inputs, but actually doing it at the level of the model. And it's actually been quite rare for deep learning architectures to account for transformations of inputs. It has been looked at a couple of times, most notably 2 years ago with spatial transformer networks from Google DeepMind, which looked at mapping inputs back to a canonical representation. So you want to build variability in the model, invariance into your model by considering a mapping in some feature space back to essentially a canonical example. Here we're doing something slightly different. Instead of trying to contract the space, we're looking at expanding the space inside the model. So I'm going to talk today about two ideas we've pursued. The first is inspired by something called mental rotation, which is the idea is if you go out and ask people to compare examples, they will mentally simulate some sort of transformation between these examples in their heads. So Roger Shepard and Jacqueline Metzle were first to formalize this in the 70s by carrying out a series of experiments in the lab. So they brought people in. Who's heard of this experiment back in the 70s, the mental rotation? Okay, a small amount of people. Okay, so let's go over it. They brought people into the lab. There were two levers, and they asked the people to look at a pair of objects and pull one lever if they were the same object, and pull a different lever if they were a different object. And they showed them three types of different objects. The first row shows the same object, but it's undergone an in-plane rotation. Okay? The second row, again, is the same object, but it's undergoing a rotation around the vertical axis. And the third row are mirror image objects, so they're not the same. So ideally, if the person's doing the right thing, they're pulling the yes lever for the first two rows, and they're pulling the no lever for the bottom row. And what Roger Shepard and Jacqueline Metzle found is that the time that it took for people to make a response was linearly related to the amount of rotation between the actual objects. Again, the fit was quite good here, and obviously there's multiple explanations for this phenomenon, but the simplest one, and actually one that was offered by the people that were in this experiment, was that they mentally rotated one object into the other when they were considering whether they were the same object or not. Okay, so if we had some sort of rotation invariant representation happening here, we shouldn't see such a clear relationship between the amount of time to make a decision and the angle of rotation. So a couple years ago, working with Gavin Ding, who's here, we thought of this idea of doing a type of mental rotation in a similarity learning model. So you're asked to compare two examples, and what you want to do is instead of just comparing these examples in some feature space, you allow one object to morph into the other one while doing this comparison. And the key thing here is that similarity learning models or transformation models are extremely powerful, so you could essentially morph one object directly into the other, and that wouldn't reflect a natural transformation, so we have to put a limitation on what kinds of transformations are possible. In other words, we can't just have ink sort of magically going from one object to one image to the other. We have to respect some learned model of natural transformations. So, for example, we have these two images, and we allow one to transform into the other by a type of transformation that we've already seen before. In this case, it's rotation. Okay? Now, there's two key components of such an architecture. One is a similarity model. So this model takes pairs of inputs, and it assesses their similarity in some feature space. So most of you that have worked in vision before know that the first thing that might come to mind for comparing inputs is just Euclidean distance in pixel space, but this is not really a good measure for capturing perceptual similarity. It might highlight color structure or global contrast effects, but ideally what you might want to do is learn some mapping to a low-dimensional space in which you can compare images efficiently and also in a notion that reflects the sort of perceptual similarity that you're after. So it may be kind of small here to see, but you might be interested in pose. So you might want your metric to capture a notion of pose, as opposed to global image effects. So that's part one of this model. Part two is that you're not just going to compute a static similarity measure, you're going to allow the images that are being compared to transform in the style of mental rotation. And what we do here is we use a type of model called a relational model. While I was here as a grad student, I worked on these types of models. Also, Roland Mimicevic, who was at Montreal formerly and now is back in Toronto, he also worked on a lot of these models as well. The idea here is you can take pairs of examples and use features or hidden units to represent the transformation between them, rather than simply encoding their content into the hidden units. Okay, so the key parts of this model is essentially taking a similarity learning or feature extraction model and a transformational or relational model together and wiring them up. So you'll see here on the left, that's a relational model. That's the part of the model that has seen pairs of images, how they transform, and learned about the manifold of valid transformations. Again, it's the idea of allowing to see things like rotations or camera angle changes or changes in lighting as opposed to just morphs of pixels. On the right, you have a feature embedding of the transformed image and the image to which you want to compare, and you compute a distance between them in some feature space. Okay? So here the notation I'm using is alpha to be one image under comparison, beta to be the other image under comparison, and we're going to let alpha transform via the relational model, for example, through rotation or camera angle change or lighting, and then be compared against image beta in some feature space. Okay? Now, what I haven't mentioned is what we use for F, which is the mapping from pixel space to the feature space where we're computing how similar these images are to one another. And essentially, I'm going to allow F to be any linear or nonlinear mapping. I mean, it could be something as simple as PCA. It could be something as complicated as a convolutional neural net. It could be trained by unsupervised learning. It could be trained by supervised learning. The idea is that you're mapping pixels into some space where you can efficiently compute their distance. Similarly, the function that or the metric that we're using to compute distance can also be any pairwise distance, but we're actually going to assume that we compute a Euclidean distance in this feature space because the feature mapping has already taken care of that problem with perceptual similarity. Okay, so this is the single-sided model because only one of the images is transforming to do the comparison. We also have a version of this called the dual-sided transformation, which is just a very small tweak on the first one, which is both images can transform to be maximally similar to one another in feature space. So here you have a relational model on both sides, and it's actually the same model. So you don't have any additional parameters when you introduce a dual-sided transformation, but now you allow both image alpha and beta to transform via some hidden units in a realistic way, and then you're going to compute the distances between them in some feature space. Okay? And that's going to be the notion of transforming distance. It's sort of a dynamic distance metric. Now, what happens when you're actually running such a metric at test time? You're going to have image alpha, image beta, and you're going to optimize the hidden units, H alpha that you see at the top there. You're going to optimize those hidden units to make the features between those images, once they've been transformed, maximally similar. Okay, so you're going to run an optimizer, manipulate the hidden units controlling the transformation. In this case, I'm showing a single-sided model, but it could also be a dual-sided model. And like I mentioned before, we don't want to accept just any arbitrary transformation of sort of a morph of one image to the other. We want to impose a regularizer which says respect the relational model that's been trained on pairs of images so that it performs a reasonable or likely transformation that we've seen in some training data. Okay, so we've evaluated this idea on two data sets. So the first domain is the Toronto face data set. Typically this data set is used for facial expression recognition, but we actually did KNN-based identity recognition. So the idea is, think about you start work at a new company, they take a picture of your face on day one, and now you're going to come back wearing different clothes, you're going to have a different facial expression, and they're going to do a biometric type of test to sort of match you versus the database of everybody whose picture they've taken. We had to do our own split for this data set because typically people consider expression recognition and not identity recognition. And we do KNN-based identity recognition because this is a reasonable way to evaluate a distance metric, which is what we're interested in here. So we've also run experiments on NORB, and in this case, the typical test for NORB is object class recognition, and we're using the usual split for NORB because this is the typical problem that's considered under NORB. So while as in TFD, the transformation that we're essentially allowing for is expression change, in NORB, the transformation that we'd be allowing for are objects under just different azimuth changes or rotations. Now, one thing that's inspired future work that I'll be talking about is a baseline that says essentially these relational models that we've been using to enforce realistic transformations are generative. So we could actually generate a much larger data set by sampling from the relational model. So we've trained it on pairs of examples, for example, facial expression changes or rotations, and then we can take an item in the training data set and generate a new version of it undergoing some realistic transformation. And the baseline that we use is we essentially increase the size of our KNN database tenfold by using these synthetic transformations. So there's a couple there's a couple key messages here. The transforming method works better than the augmentation baseline, and that works better than the baseline, which is just a regular KNN-based distance metric. But what is interesting is when we start to look at changes versus K. So when we're doing KNN, K-nearest neighbor recognition, we have our database. If we are looking at the Toronto face database, what we have in these two splits is either a single example of someone's identity in the database. So for example, they took your picture at the day you started work, and that's the only image they have of you, so there's just a single match in the database. That's K equals 1. There's also the idea that we have up to 4 of the same images of a person in the database, so there's more examples, and the relational model has been able to see every single person. So that's the TFD split 2. It's a little bit easier a problem. However, in both of these cases, there's a very limited amount of examples for a person in that database. And so when we increase K, which is the number of hits you're allowed to make in the database to vote on the identity, we see the performance drop off the traditional metric, as well as the transforming distance. Now, when we synthetically augment our KNN database with examples of people under different expressions, or in the case of NORB, people and objects under different rotations, we see that we actually don't drop off in terms of performance with K. So augmented KNN is actually able to allow us to work under higher settings of K. With NORB, we actually see that because we start with a larger number of the same class objects in the database, using the transformed version of KNN, we're able to match with objects of various transformations within the database, not just the exact type of rotation that was present in that test example. When we're working with a reduced data set, in terms of the number of examples in the database, we found with TFD, we could actually, using transforming distance, reduce the size of the database down to about 70 or 80% of its examples and still compete with the standard KNN metric. When we look at NORB, we're actually able to reduce the size of the database down by 99% of the examples when using the transforming distance, because it's essentially allowing us to change the query image in the way that it can match against other objects and the same object in different rotations. So this is important for distance metric learning methods or KNN-based methods because the time it takes to do a match in these sorts of systems is quadratic in terms of the number of examples in your database. Okay, so that's one idea using mental rotation. The second idea in terms of dataset augmentation goes back to the idea of manipulating images in a domain-specific way in the input space. Something you might consider is just doing something much simpler, which is, what about taking inputs and simply interpolating between them? So the idea is you have, for example, two classes here. You have a very rare class, you have a common class, and let's take your examples in your rare class and start generating synthetic examples by interpolating or maybe even extrapolating them. Okay, so this is known as synthetic minority oversampling. It's a commonly used method for the case of imbalanced data. The problem is for high-dimensional inputs like images, it doesn't work very well. So this is a figure from a paper by the Bengio group a couple years ago. And this shows very nicely that when you try to interpolate in pixel space, you get images that don't look like the domain at all. So for example, we have MNIST digits. We have a manifold of 9s, a manifold of 3s. We try to interpolate between them, and we get something that doesn't look like a 9 or a 3. The argument for this is that simply when we look at high-dimensional data, it's a very twisted, complex manifold, low-dimensional manifold in some high-dimensional space, and therefore when we interpolate in this high-dimensional space, we end up with it's being very likely to land on a point that doesn't exist on either manifold. Now what happens is when we do representation learning, we smooth out and we expand the volume of this space such that we start, if we do interpolation at the hidden layers, we actually start generating resulting images that look like the domain. So if you're doing interpolation at the second layer of something like an autoencoder, you'll get something that actually looks like somewhere between a 9 and a 3. Okay, so that just motivates the idea of why don't we consider doing augmentation not in input space, but in a very generic way in feature space. Okay, so instead of doing a very specific type of transformation like adding domain-specific noise or doing a cropping or a scaling, we're going to consider a very simple type of transformation in feature space. Consider adding a generic type of noise like Gaussian noise. Consider doing an extrapolation, or consider doing an interpolation in feature space. And of course, we could use any type of representation learning architecture. It might be an RBM, it might be an autoencoder, it might be a generative adversarial network or variational autoencoder. We could choose any type of representation learning architecture we desire. But what we've proposed to use is a sequence-to-sequence autoencoder because it can adapt to both static data or sequential data. And so this is a commonly used architecture for ResNet machine translation. The idea is that you have a sequence coming in, you have a sequence going out, and you have a hidden state representation that allows you to do a mapping from one input or one sequence to another sequence. So for example, you can put an English language sentence in, you can get a French language sentence out, and you have a hidden state for both the input and the output. Now the interesting thing here is that the final hidden state vector after observing the input is something called the context vector, and that captures everything that's necessary to perform, for example, the translation. In the case of training a model like an autoencoder, we have an input sequence coming in, and then we have a reconstruction of that input going out. And therefore, this context vector, the last hidden state after observing the input sequence, has to capture the information necessary to perform an accurate or complete reconstruction of that input. And so that context vector, that last hidden state step, is what we're actually going to use for the augmentation. We're going to manipulate that in feature space. Okay, so for a quick overview of the method, we're going to train a sequence-to-sequence autoencoder on the training data set. Then we're going to have a method by which we can map any sequence to this vector representation called the context vector. And then in context vector space, what we can do is do interpolation between context vectors in the same class, or we can do extrapolation between them, or we can add noise to them. And this will generate more context vectors. And then we can do in the last step of two things. We can either decode those context vectors back to sequences using the decoder, or we could train a model directly on the space of the context vectors and do classification from that step. So just as a few visualizations of this working in practice, we might take a series of Gaussians at different frequencies and amplitudes and phases. So for example, in the top the top plot, you see a dark blue line representing one sinusoid. You see a dark green line representing another sinusoid. These have been mapped to context vector space using the sequence-to-sequence autoencoder. We've added Gaussian noise, and then we've decoded them. And so in each case where we've added noises, you see they still retain the fact that they're sinusoids. If we do interpolation between two different sinusoids in context vector space, we get what we would expect to have is essentially an interpolation in the space of sinusoids, and we can do the same thing with extrapolation as well. It still maintains its identity as a sinusoid. We can also take sequences of people drawing characters. These have been captured with a pen tablet, and here you see in the top row and the leftmost column essentially the parents. These have been mapped again to context vector space, and here in the top they interpolate between them, or we extrapolate between them, but these still maintain identity, in this case as at character. And the other thing I would point out here is that when we extrapolate, you see a lot more variability in the results. So this is already a key to what's going to work better in practice versus extrapolation versus interpolation. Okay, so the key messages in terms of running some experiments. In all cases, we've used a sequence-to-sequence autoencoder approach. We've used a very simple classifier trained directly on the context vectors, and we've measured how the method performs either as a baseline with no data augmentation in input space versus data augmentation using some generic method in feature space. And in a speech domain, in hand motion capture domain, and in a full body motion capture domain, we always have seen benefit using extrapolation in feature space. What's interesting here is noise doesn't work very well. Interpolation doesn't work very well because the interpolation really has the effect of contracting the space rather than expanding the space, which we observe in extrapolation. So in all of these methods have used very generic classifiers, which are just MLPs trained directly on context vectors. So none of them are beating the state of the art, but they're consistently showing a benefit of using extrapolation. Now, the nice thing I mentioned about the sequence-to-sequence autoencoder is you can also use it for static images, or static data like images, where you take a pixel stream and you map that through a sequence-to-sequence model, and that gives you a context vector representation of that image. So we've tested this also on MNIST and CFAR, where we use an MLP trained on top of the context vectors that have been extrapolated in feature space. So again, we see a benefit versus doing input affine transformations on MNIST. And in the case of CFAR, it's common to do some shifts and mirroring, which is just sort of data augmentation in input space. And we see that doing extrapolation in feature space is actually complementary to doing direct manipulation of the data in input space. Now, for CFAR, this architecture is not very competitive. So when I showed this at NIPS at the CFAR meeting, the primary comment I got is, this is not state-of-the-art performance on CFAR. It's actually quite poor performance on CFAR because we're training a very simple MLP on top of context vectors. So the best performing methods are variants of convolutional nets. So we've gone back and we've trained a competitive or a state-of-the-art type of architecture, which is wide ResNet, on these models, where instead of using an MLP on the context vectors, we've decoded the extrapolated context vectors, and then we've fed those as input to the convolutional neural net. So what we see in this case was actually somewhat disappointing. Extrapolation in feature space didn't outperform the standard data augmentation, but we suspected there might be something that has to do with the fact that we're reconstructing the data and there being something sort of in terms of the fidelity of the reconstructed data as input to the system. So what we further investigated was actually what happens if we take the original input data, map it through the sequence-to-sequence autoencoder, and then reconstruct that and feed the original data, which has been reconstructed, as inputs with and without augmentation. So we see that just using reconstructed original data, which is line 2 here, actually severely impedes the performance of the model. if we use a mixture of standard data augmentation on the reconstructions as well as extrapolation, we see there's actually an improvement using extrapolation in this effect. But that's essentially where we're at right now, is there's something about the use of the reconstructions that's hurting performance considerably. So I'm out of time. I'm going to summarize the idea of data-independent generic transformations in feature space. I talked about the first idea of learning a transformation model, where you explicitly show the model examples of inputs undergoing transformations, learn about those transformations, and then allow a model to permit the transformation of examples during comparison. That model required us to collect a data set of images under transformation. So that's the downside. The second idea was a more generic method where we didn't have to collect a specialized data set of transformations. We simply used a generic representation learning technique and then performed very simple transformations in feature space. We used a sequence-to-sequence autoencoder, but of course you could use various unsupervised representation learning methods. We saw it working in 4 different domains, both sequential and static, using the same simple architecture. It has complemented domain-specific augmentation on the CFAR dataset. And one use of this may be as a method for evaluating unsupervised learning techniques. So the jury's still out on the best methods to evaluate unsupervised learning, and also what we can use unsupervised learning for. So this perhaps satisfies both properties. And with that, I'd like to acknowledge Gavin, who's here, and Terrence, who worked on this project. And I would be very happy to take any questions you might have. I haven't. Okay, so the question is, could we use this in terms of adversarial training? And you also mentioned adversarial examples. So there's the idea that, so adversarial examples. Okay, so the idea here is that people have shown that you can sort of run an optimizer over pixel space to sort of change the outputs and create these examples that essentially fool your network. I think many of you have probably seen this. You make very small manipulations in pixel space that creates images that are essentially indistinguishable from the training images, but those produce very different outputs. So, I mean, we're talking about doing some sort of transformation in feature space that will produce, images that still look like the right class, the right domain when they're reconstructed. So, yes, I mean, you may incorporate, say, a term in the whatever objective you're using to control the transformation that may assist you with being resilient to sort of spurious outputs. Something I didn't mention is sort of the natural extension of this, which is not using a fixed transformation, but actually learning the transformation. So maybe we could actually learn the transformation operator in feature space with a criteria to make the model resilient to these sorts of fooling examples. We haven't explored it, but certainly the idea of learning the transformation operator instead of using a fixed one is one that we're pursuing now and interested in. Yep.
We use a lot of transformation as conceptually good at work. Is there any interest in trying to apply like things that we conceptually understand, like a spectral domain transformation for it?
Okay, so I think your question is along the lines of a lot of the examples I was using were domains like images where we can visualize the transformation and understand them. And actually, the thing is with images, this is where we can augment data directly in input space because we know how it should be manipulated. But you mentioned other things like, say, a spectral domain where it would be very difficult to engineer a technique to do the transformations. I mean, that's certainly the motivation of this work. We're primarily a group that works in vision, and these are the sorts of data sets that we're familiar with. And these are the sorts of architectures that we're familiar with as well. But really the motivation here, we did look at some motion capture as well as speech, smallish data sets. But something that has come up a lot is people asking about how this would work, for example, on text. Because people have more of a difficulty understanding how you might design sort of ways to manipulate text directly. So yeah, I mean, the answer is this is where we actually think this would be useful in different types of data domains. I mean, one area that we are working is is in remote sensing, where people are using perception beyond the visible spectrum, and this, I think, might have an advantage in that space. We haven't carried out those experiments yet, but we hope to go there. Yeah, go on.
For the extrapolation, are you only doing pairwise extrapolation, or you are doing a common?
Yeah, I didn't talk a lot about the details of the extrapolation. So Gavin's asking about how we're actually doing the extrapolation. We're taking just pairs right now. We're just doing pairwise, and we're always selecting examples in the same class. We tried it with different class. It didn't seem to be as valuable. We're finding nearest neighbors. In the small data sets, we just do a brute force nearest neighbor search. In the larger, for example, image data sets, we're using approximate nearest neighbors, where we can we don't have to do sort of an n-squared search. So we find approximate nearest neighbors in the same class and do an extrapolation. Now, the other thing I didn't mention is how much we're extrapolating. That's obviously a hyperparameter. We're looking at the distance between two examples, so the two parents, and we're not extrapolating more than that distance. So we're extrapolating. So if you consider the distance as 1, we're extrapolating some fraction away from either image. And I guess you saw that in the last slide, the visual results of extrapolation on CFAR. So for example, extrapolating between these two images of cars, more in the direction of, in this sort of beyond the direction of this, towards this image, you get something that sort of enhances the blue background that's here. If you have sort of a black and a brown horse, there's a sort of a grayish horse, and you extrapolate between them in the direction of the grayish horse, it actually makes it more like a black horse, but maintains the background. So it actually seems to be doing the extrapolation in some sort of visually reasonable way. And of course, there is a hyperparameter there in terms of how much extrapolation to do. You have to cross-validate that. Other questions? Yep.
How did you find the performance of the model change with the amount of data you were gathering? So how much did you use that, or how much was too much?
So we haven't done extensive experiments with looking how this might, so it's at least for the second part of what I talked about, which is extrapolation, how this might help in sort of low training data scenarios. It might be something to look at. In terms of how much additional data you add to the model during training, again, this is something that gets cross-validated. I don't have any plots. I mean, it may be a nice plot to make. It's a great suggestion of sort of the amount of extrapolated data you add to your data set and how that would affect performance. So thanks for the suggestion. Yep.
Thanks for the nice talk. We were just discussing how do these kind of algorithms deal with biases in the data. I know that most image databases are huge, so the biases are fairly small. But if you go want to use these kind of techniques for other data sets where you have huge biases, like biomedical data, for instance, do you think that might be a problem, or do you?
No, it's similar to the question that came up before in terms of, I mean, we are showing it sort of on generic visual recognition data sets. People understand that space. We actually think this sort of method would shine in sort of specialized data sets, for example, in the medical space, where people can sort of inform the model using, say, their biases or their prior knowledge of those data sets is actually in constructing the transformation model. So, you can either look at constructing we're talking about here noise or extrapolation or interpolation. You could modify that to be to incorporate knowledge of your domain, or if you had a reasonable amount of data, as I was saying before, you could learn sort of the ideal transformation operator for that domain. I mean, people in I gave a talk at a Western a couple of weeks ago where they have a big medical imaging research group, and they seem receptive to this idea because you maybe work in medical imaging yourself. Like that's a major problem, right? Access to large labeled data sets. Yeah.
Quick question. What I'm interested is, people have a genomic data or sequencing data. I was thinking like, especially genomic data, there are what we call batch effects. So there is a output of class that we are interested in, but besides that, there can be something, the artifacts of the experimental technique used to produce data, something, that is associated in the given laboratory where the data were produced. So I'm afraid that I would employ some of the techniques you just described. I would amplify those effects incredibly. So I would extrapolate just based on samples from some laboratory. And those hidden biases can be amplified tremendously.
Okay, I must admit I was having some problems hearing everything, so I'm good. The gist I got was that there may be existing biases in your data set, maybe in terms of that domain or the way that the data was collected, and doing something like interpolation may amplify those sorts of biases. Yes, it could. And we haven't tested on genomic data, we haven't tested on textual data. And we love to either try that ourselves or have other people investigate this. Now that may be how this performs or how it responds to this notion of amplifying biases. That might also depend on the particular type of representation learning technique you select. We found something, the sequence-to-sequence model, that tended to work across multiple domains, but you may find that particular technique doesn't work for your specific domain. Thank you.